considering this last problem we just did, we realized that it's actually an example of a composition one, where we put one function inside a known power series function. So this was an example of composition example, which is case 3 from that theorem. So now let's see a different type of case. So we have 2x squared, oh, look at that, over 1 plus x cubed. But we know what 1 plus x cubed is. So this would be the same as 2x squared times 1 over 1 plus x cubed, right? So we know how this is going to go. This is 2x squared times, and then we know what this series is because we just built it in the last example, which it's from k equals 0 to infinity of negative 1 to the k, x to the 3k. And then our interval of convergence was for the absolute value of x is less than 1. Now, I want to now add in the 2x squared piece to this. So I had an x squared here, and I have an x to the 3k over here. So I want to pull that in and put those pieces together. So that's going to make a new series, which is 2, still sitting out in front. I mean, if you want, you could put it inside. It's not going to hurt anything, but 0 to infinity, negative 1 to the k, so it's an alternating series, x to the 3k plus 2. And we haven't really affected our interval of convergence, although we could check it. Right, we think it's going to be for the absolute value of x is less than 1. But I can check the endpoints just to make sure before I walk away from this problem. So let me check them briefly, because I did change what this looks like in here. So I should probably check just to make sure. I affected the term that has x in it. So x equals negative 1 would look like 2 times the sum, I don't really care about the 0 infinity part, negative 1 to the k, and then it would be negative 1 to the 3k plus 2. So that would be 2 times negative 1 to the 3k plus 3. No, it's not. It's 4k plus 2. What am I doing? K plus k. You're adding the powers. Sorry. 4k plus 2. There we go. Well, that diverges, right? It's not going to pass the divergence test again. And then x equals 1. I'll say diverges in just a second. It'll be 2, then be negative 1 to the k, and then 1 to the 3k plus 2. But 1 to the 3k plus 2 is always 1. So this is really 2 times the series of negative 1 to the k. Both of these diverge. So we're done, right? So this actually is the correct interval, like there, with no less than or equal to's. Now, what type of case was this? What did I do? Well, I'm taking a known power series and I'm multiplying it by a polynomial piece. Well, it's really a single term, x to the power. So what I'm doing is multiplication, right? I'm taking x to the 2, well, 2x to the 2, and then I'm multiplying it by my power series. Right? The 2 itself as a constant is not really a big deal. You can kind of stick it wherever. You can think of it as this or that. It doesn't make any difference, right? So the important part is the x squared part. And then I changed it to the x to the 3k plus 2 because this was x to the 3k right there. Right? So this was case 2. This was multiplication by a power. Well, I guess by x to the power. Right? All right, now let's look at this example. So I have x over 5 minus x. Ooh, interesting. Okay, so this isn't going to build off of the one we've already done. We're going to have to rewrite this. So let's rewrite this as x times 1 over 5 minus x. Interesting. So that would be x times 1 over, and then I'm going to rearrange this. I'm going to factor a 5 out here. And that would leave me a 1 minus x over 5 in here. Okay, so that would be x over 5 times 1 over 1 minus x over 5. Now, why am I interested in this? Well, because this one, I can use the series that I already know, which is the only series I know at this point, the geometric series that I highlighted on the previous page. 1 over 1 minus x would be this power series. So I'm going to have x over 5, so it's going to be x over 5, but other than that, it's the same series. Right? Okay, so let's do that. So the power series is going to be equal to, I'm going to have an x over 5 in front, and then this part right here I'm going to turn into my geometric series. So it's k equals 0 to infinity, but instead of x to the k, I'm going to have x over 5 to the k. Right? I'm following the form of the geometric series that I know from the previous page. All right, now when would this reduce? So if you look at the geometric series, 1 over 1 minus x, converges to, this series converges to that function for this interval. But I don't have 1 minus x. I have 1 over 1 minus x over 5. So it's going to be x over 5 is less than 1. Like that. Okay, so what would this look like? Let's do a little bit of, well, algebra. A little bit of calculus and algebra. So I'm going to put k equals 0 to infinity. And I guess I'm just going to put these together. X to the 1 times x to the k is x to the k plus 1. Similarly, 5 to the 1 times 5 to the k is 5 to the k plus 1. Like that. And then it's going to be convergent for the absolute value of x. I'm going to try to solve this for x. So I'm going to multiply both sides by 5. I don't have to worry about the absolute value because 5 is positive, so it doesn't really make any difference. So 1 times 5 is 5. So there's my power series. Now I'm not 100% sure about that interval. I'm going to need to check my endpoints before I truly circle it and walk away. So I did circle it, but I want to check. All right, so let's check those endpoints. Because it's possible I'm going to have to change that interval to have one side include a less than or equal to or something like that. All right, so I'm going to have to let x be, just remember what this is here. So this would be the absolute value of x is less than 5, which is negative 5 is less than x, which is less than 5, right? Matter of fact, I'll just leave it like it is, but they're one and the same. Okay, so let's check the endpoints. Let's put in negative 5 into our sum. So we would have a sum, you're putting negative 5 into here. So it'd be negative 5 to the k plus 1 over, why did I write it like that? That's silly. I wouldn't have done that. I'm sorry. I missed a step here. It was correct. It's just, why would you write it like that? Why wouldn't you write it like this? Right? They're both k plus 1, right? Okay, so, I mean, you can leave it k plus 1 if you want. So it's negative 5 over 5 to the k plus 1. Or if you like, negative 5 to the k plus 1 over 5 to the k plus 1. Either way, you could end up with negative 1 to the k plus 1. That diverges, right? It fails the divergence test. So diverges for sure. That limit is not 0, not even close, right? And then if x equals 5, I would have a sum of 5 over 5 to the k plus 1. That is the sum of 1. I mean, if you want to say to the k plus 1, fine, but it doesn't really matter since they're all 1s. That also diverges because 1 is not 0. I mean, if you remember the divergence test, that sequence has to go to 0. Otherwise, it diverges. That's the divergence test that we learned back in chapter 10, right? We have to have the sequence that builds the series go to 0. And that is completely and totally not happening here. So both of those diverge. Therefore, this interval that I've written actually is correct. -5 is less than x, which is less than 5. I have the power series and I have the interval all circled. But you do always have to check endpoints. You never know. One of them might converge. So you have to do it and show the work for it if you're turning in the sheet.